Hello, today we are moving to section 11.4. Section 11.4 is exponential and logarithmic functions. Here we are going to talk about graphs and orders associated with them. This is chapter 11, analysis of algorithm efficiency. I split this section into two parts. So today I'm going to teach the first part of the section. This section is an easy section. This section covers logarithmic functions that everybody knows. Let me to read this. Exponential and logarithmic functions, graphs and orders. Exponential and logarithmic functions are of great importance in mathematics in general and in computer science in particular. But let me do a small change here. All right. All right. So now it reads well. Exponential and logarithmic functions are of great importance in mathematics and in computer science. All right. So let me take this out too. In particular. All right. All right. Great. Several important computer algorithms have execution time that involve logarithmic functions of the size of the input data. All right, so you know this. So there are some algorithms, computer algorithms. Their computational time is expressed as a logarithmic functions, which means that they are relatively efficient for large data sets. That's true. If you have an algorithm which has logarithmic computational time, then it is fast because logarithm makes the computational time significantly small. All right, as an example, let's say this number 10 to the power 10, this is a big number. If you take the log of that, this equals just 10. All right, so once you get the logarithm of that, so that number becomes significantly small. All right, so it give me a second. Oh, I don't know, my pen does not work. All right, you have seen that taking logarithm of this big function makes the function very small. Okay, which is 10. All right, so now we understand logarithmic functions are very important in computer when you compute complexity of computer algorithms. All right. Some have execution time this is the case where the computational time is a logarithmic function. Let's move to the next case where we discuss the computational time is an exponential function. Some have execution time that are exponential functions of the size of the input data, which means that they are extremely inefficient for large data set. All right, they are extremely inefficient. In the previous case, they are relatively efficient. All right. In this case, you could take n to be 10, and then you could write the exponential function as 10 to the power 10. Okay, so this is a big number. This is a big number here. In the previous case, it was a very small number. All right, so let's move to the next slide. Let me mark this right here. In addition, since exponential and logarithmic functions arise naturally in the description of many growth and decay processes and in the computation of many kinds of probabilities, these functions are used in the analysis of computer operating systems in queuing theory, computer operating systems, queuing theory, and in theory of information. All right, those are the fields that we have applications of logarithmic functions. Let's go down. The exponential function with base b greater than 0 is the function that sends each real number x to b to the power x. Alright, so you have x here, you have b to the power x here. Exponential function just send this x to b to the power x. The graph of the exponential function with base 2 together with partial table of its values is shown in figure 11.4.1. All right, so now we are going to talk about an exponential function with base 2. Here the base 2. All right, so you see the base right here. Base right here. Now you have the x values in this column, and then you just take 2 to the power x. So you have these values. All right, so I plot that in this right hand side graph, so you see this behavior. So the exponential function is a rapidly increasing function. Okay, so rapidly increasing function when b is positive. When b is negative, it's a rapidly decreasing function. Okay, it's here rapidly increasing. All right, let's move to the next slide. Graphs of exponential functions. There are four bullet points here. Note that the value of this function increases with extraordinary rapidly. All right, so you understand it increases in a rapid pace. If we try to continue drawing the graph using the scale shown in figure 11.4.1, that is the scale here, we would have to plot the point this more than 20 feet above the horizontal axis. All right, so this number when x equals 10, this is the case where x equals 10. You have to draw this point when x equals 10, 1 feet above the horizontal axis. All right, then go to the next point. At the point this 30 comma 2 to the power 30, that means x equals 30, would be located more than this miles higher, more than this many miles higher. Actually, that is beyond the moon. That is beyond the height of the moon. All right, you can see how rapidly it grows. Okay, when x equals 30, the point is well above the moon. So it is growing very rapidly. Those are the exponential functions. Those are the bad behaviors of exponential functions. The graph of an exponential function with base greater than 1 has shape that is similar to the graph of the exponential function with base 2. Okay, normally the shape is always same for all the exponential functions where b greater than 1. For all the cases where b greater than 1, we have the same shape. Okay, same rapidly increasing shape. With same rapidly increasing shape. All right, so keep that in mind. Go to the next slide. If b is in between 0 and 1, then 1 over b is greater than 0, that is clear, and the graph of the exponential function with base b is the reflection across the vertical axis of the exponential function with base 1 over b. Alright, so this is something very interesting. Here it is like this: y equals b to the power x, where b is greater than 1, then the shape will look like this. When you have y equals bx, where b is between 0 and 1, the shape is actually like the mirror image. If you just keep a mirror here, let's say you keep a mirror here. Let me draw the mirror like this, maybe like this. It's a mirror. Okay, so you see the mirror image of one function in the other side of the other function. All right, so the only change is b. Here b is greater than 1. Here b is between 0 and 1. All right, let's move to the next slide. Logarithms were first introduced by Scotsman John Napier. Astronomers and navigators found them so useful for reducing the time needed to do multiplication and division that they quickly gained wide acceptance and played a crucial role in the remarkable development of those areas in the 17th century. All right, so I don't know whether you remember this. In olden days, we use logarithms to simplify big numbers. Okay, we use logarithms to simplify big numbers. As an example, let's say you are asked to compute these two numbers, 10 to the power 1.5 times 10 to the power that. So this you have to compute this value. Since both are to the base 10, it might be easy for you. But let's say you are not using the approach of bases. You are not using the approach of indices. Let's say you are using logarithmic approach. So you could write this as log y equals log 10 to the power 1.5 times 10 to the power 2700, and then you could write this as log 10 to the power 1.5, and you could write plus log 10 to the power 2700, then you could write this as 1.5 2700. So this is 2701.5. Okay, this is log y. And then you could write this as, then take the reverse logarithms of the both sides. That means the exponential. Take the exponential of the both sides. Then this equals, y equals 10 to the power 27015. So by using logarithms, you can simplify expressions very quickly, big expressions very quickly. Let me write as an example. All right, let's go forward. Nowadays, however, electronic calculators and computers are available to handle most computations quickly and conveniently, and logarithms and logarithmic functions are used primarily as conceptual tools, right? So nowadays you have calculators to do these big computations. You have calculators to do this, so you don't need logarithms. In olden days, where we didn't have computers or calculators, people just used logarithms to solve big values. All right, let's go to the definition. If b is a positive real number not equal to 1, then logarithmic function with base b is given like that, is the function that sends each positive real number x to the number log of x, which is the exponent of to which p must be raised to obtain x. All right, the meaning of this part is, which is the exponent which b must raise to obtain x. That means if you do something like this, you have log of x to the base b. If you just write b to the power log of b, let me write it a little bigger, log, sorry, I made a mistake here, b to the power log of that, this should be just x. Okay, that is what is explained by this orange color expression. All right, they are same. All right, which is the exponent to which b must be raised to obtain x. That means the reverse of logarithms. So this is the reverse of logarithm. All right, go forward. Graph of logarithmic functions. The logarithmic functions with base b is in fact the inverse of the exponential function with base b. Okay, the same thing here can be given as an exponential function. The logarithm can also be given as an exponential function because they are inversely related. It follows that the graph of the two functions are symmetric with respect to the line that y equals x. The graph of the logarithmic function with b greater than 1 is shown in figure 11.4.3. All right, so this is the corresponding logarithmic functions. You know these things, these are simply calculus 1. Let me explain a small part here. So this thing, logarithmic functions and exponential functions are symmetric about the axis or maybe the line y equals x. That means, let's say these two axes, x and y, all right, so this is that line. y equals x. The exponential function will look like this. And the logarithmic function will look like that. Alright, so this is just y equals e to the power, so let me put some b, not e. E is so specific, let me put something like b to the power x. This is y equals log of x to the base b. Alright, now you can see they are symmetric. These two are symmetric about the about this axis, about this line. Okay, it's simply this one is the mirror image of that. If you keep the mirror at this symmetric line, if you just keep the mirror here, this is the mirror image of that. Alright, so go forward. Here we have three equations which provides you three basic laws of logarithms. Let me read them. If its base b is greater than 1, the logarithmic function is increasing analytically. It's increasing analytically. This means these three conditions: condition number 1, condition number 2, condition number 3. So you have to make sure that it's increasing. Let me go through one at a time. The first condition says that's more likely the definition of increasing of a logarithmic function. If b is greater than 1, then for all positive numbers x1 and x2, if x1 is smaller than x2, then logarithm of log of x1 to the base b is smaller than log x2 to the base b. Okay, so this is more likely the definition of increasing of logarithmic functions, which is clear to you, I believe. All right, the next two things are a little bit complicated. Let me explain them. If k is an integer and x is a real number with this condition, which is 2 to the power k less than or equal to x less than 2 to the power k plus 1, then log of x to the base 2, and you have the floor function equals k. As you remember, this is the floor function. Floor of x. Okay, the floor function. As an example, if you have 1.5 floor function, 1.5 floor function, this means just 1. Then 1.7 floor function, let's say 1.7. This is just 1 again. All right, so that's the floor function. In the next condition, for any odd integer n greater than 1, the floor function of log n minus 1 to the base 2 equals the floor function log of n to the base 2. Right, there are two conditions here. This condition is easy to understand. It is easy to understand. Let me show that right here. All right, let's start showing this result. What is given is 2 to the power k is smaller than or equal to x, smaller than 2 to the power k plus 1. Alright, now get the logarithm of the entire expression. So I will write log 2 to the base 2 to the power k, log to the base 2 of x, log to the base 2 of 2k plus 1. Alright, so you have learned logarithms in Calc 1, so you can just bring this power in front, that power in front. So you write this as k times log to the base 2 of 2, log to the base 2 of x, and then here k plus 1, log to the base 2 of 2. Alright, this is 1 and that is 1. So you write this again as k log that k plus 1. Alright, so what is the meaning of this? Let me take this over there. Here you have k smaller than equal sign, and then log of that less than k plus 1. So this means log of x to the base 2 is in between k and k plus 1. You know k is an integer, alright? So we assume k to be an integer at the beginning. Alright, so that means this value is in between two integers. Okay, that value is in between two integers. This value in between two integers. Now I'm gonna get the floor function of that. If I get the floor function of that, since it was between two integers, give me a second. Since it was between two integers, so this value should be equal to the lower number. Okay, the number at the lower end when you get the floor function, because this is a number which is between two consecutive integers. So the floor function, when you get the floor function of that, so that means it should equal to the lower bound, like I explained right here. All right, let me take these extra things out. All right, so I believe everybody understood that. And then I'm going to show this thing in the next slide. Let me move to the next slide. Okay, this is what you're going to show. I have already written down the solution. Let me read it. If n is an odd integer, it is given that n is an odd integer. If n is an odd integer that is greater than 1, then n lies strictly between two successive power of 2, right? So you can write this for any odd integer. All right, take any odd integer you need. Let's say if n equals maybe 11, then you could write the same thing. You write 11 here, less than symbol here, greater than symbol here. So then you write 2 to the power something, again 2 to the power something. So you can just write this to be 2 to the power 3 is 8 and 2 to the power 4 is 16, right? This is 8, that is 16. So this happens for any two such numbers. In the next case, let's consider any other number you want. Let's consider n to be 19. Then you have 19 here, less than here, greater than there. Then this should be 2 to the power some number, maybe which is 16 here, 2 to the power, I'm sorry, not 16, 2 to the power 4, which is 16, and here 2 to the power 5, which is 32. Okay, so this is 16, this is 32. All right, so this result is okay to everybody then. Okay, then go to the next line. It follows that 2 to the power k is less than or equal to n minus 1 because k is less than n. Now let me write this. All right, let me write this. What I'm saying here is you understood that this n is an odd number. You know, this is an even number. This is an odd number and this is an even number. If you just write n minus 1, then this is an even number. Then that even number can be equal to 2 to the power k. It can be, okay. That's why I'm just replacing this inequality like that. Previously it was strictly less than, now it is less than or equal to, because I made a small change at n. Now it's n minus 1. So I can simply just replace less than symbol by less than or equal to symbol. All right. So I explained that one right here because 2k is an integer, even integer, and n is an odd number, odd integer. Okay, so then you can write the same expression like this. Now you have n minus 1 here and less than or equal to symbol over there. Okay, so you have this right there. The reason that we make here is, we could use the property 11.4.2. Okay, so this is 11.4.2. We could use this property if we have equal sign at the lower bound. So this is the lower bound, we have the equal sign. So we could use that property. That's why we made equal sign right here. Okay, so we could use this property. Okay, then by using that property we write, give me a second. By using that property we write log of x to the base 2 equals k. Okay, here it is simply give me a small, let me take this part out. It is not clear. So then I write, and okay, so this part is supported by that property. K equals log of n, which is this property. And then Here actually I forgot to state what are these equations are. First of all, let me mention what are these equations that I forgot about. Sorry about that. So actually 11.4.4 is this equation. 11.4.4 is that, and this is 11.4.5. Alright, now it's clear now. So this equation is that, and this equation is this. Alright, now since I marked the equations, let me make a small change here. Actually this condition supports property 11.4.2 supports for both of these, this as well as that. It supports to both of the conditions here. All right. This is provided by that. Let me use different color. These two are connected, and then let me set another different color. These two are connected. All right, let's go back to that property right here. And this is the corresponding property we are using. You have 2 to the power x, 2 to the power k, less than or equal to x, less than or equal to 2 to the power k plus 1. And then you have floor log of x to the base 2 equals k. So that is the condition over there. That condition directly supports this idea, because you have this less than or equal sign, so it directly supports that claim. And the problem is how this, you might feel like how this supports to that, because no equal sign here, no equal sign there. That's fine. Even though you do not have equal sign here, you could replace that by equal sign. Okay, no harm. You could always replace that by equal sign. So you could write this as 2 to the power k less than or equal to n less than 2 to the power k plus 1. Okay, so you could write this condition for that. There's no harm. Equal less than or equal to means it has less than sign, of course. Okay, so you could just replace that by less than or equal to sign. That means you could just use give me a second. You could just use this previous property for both of the places. Could use this property for both of the places below. All right, so this then you have these two conditions, one condition here, one condition there, and then you combine them together to get that. Okay, here you have k, here you have k. Sorry, the pen doesn't work. Here you have k, there you have k, then you can just replace k. You can just replace k and then write this final equation, which is what we have to get. All right, so that is the condition we have to show here. Okay, let me move to the next slide. In the next slide, we are going to discuss an application. Number of bits needed to represent an integer in binary notation. All right. So here the problem: any positive integer n can be written in a unique way as this, where k is a non-negative integer and each c naught, c1, c2, blah blah blah, ck minus 1 is either 0 or 1. Then the binary representation of n is given like that, which is the binary representation of n. And so the number of binary digits needed to represent n is k plus 1. There should be k plus 1 binary digits required. All right. What is k plus 1 as a function of n? All right. So this is the question that we have to answer here. First of all, let me explain how binary number representation work here. Computer science students know this. Let's say you are given example. Let's say you are given number 5. Number 5 can be written as a binary representation. For that, you just multiply with 2 to the power 2, which is 4, plus, and then this will give you 4, and then you have another 1 remaining. Then 1 times 2 to the power, let's say 0 times 2 to the power 1 plus 1 times 2 to the power 0. All right, so this is the binary representation of 5. Thus, 5 can be represented as represented as 1, 0, 1. You take 1 from this, 0 from that, 1 from this. Okay, so that's the binary representation of 5. Let's get another number, maybe 11. 11 can be written down as 1 times 2 to the power 3, which gives you 8. And then 1 times 2 to the power 2, which gives, give me a second. Here you have 8. Here, okay, it's too much. Then 8 plus 4 is 12. So let me put 0 here. 0 here. And then plus 1. 1 times 2 to the power 1 plus 1 times 2 to the power 0. Okay, so that will give you 11. So the coefficients that we get is 1, 0, 1, 1. Thus, 11 can be represented as 1, 0, 1, 1. Okay, so those are the binary representations. That's what we are explaining right here, the same concept. Okay, for the first one, we always keep 1 here. Let me do this here. Here we always keep 1 for the first digit. We keep 1 for the first digit and then we change the rest accordingly. All right. So now the question is this. And the question is, what is k plus 1 as a function of n? All right. So that is what we're gonna find here. So n and k are related here. N here, k is here, so they are related in this very first equation. Now we have to find k plus 1 as a function of n. All right, so let me go step by step. For that, we're gonna make two inequalities here. Observe that since each ci equals 0 or 1, we have this condition. You could write n like this, that we have done already. Like this. You could replace all these c values by 1, because c's are either 1 or 0. If you just replace them by the largest possible, then you get this series, but you have to replace the greater than or equal to sign here. Okay, it is greater than or equal to. Let me emphasize it. This is greater than or equal to, because you are replacing all the values here 1, here 1, here 1, here 1. You replace all the c values by 1, by ones. All right. Now this series, which is familiar to you, this series is called geometric series. This is a geometric series. Okay, let me write geometric series. It's a geometric series. You know how to compute sum of a geometric series, which is given right here, that we have learned in Calc 1. This is a geometric series. You could just use this formula to compute that. It is actually 2 to the power k plus 1 minus 1, 2 minus 1. So this is the equation for that. And then you simplify this as that, because 2 minus 1 is 1. You divide that by 1. That means just this quantity. All right, so now you have found the sum of that, which is 2 to the power k plus 1 minus 1. Then we write n, which is right here, n, which is smaller than or equal to 2 to the power k minus 1. And this can also be written down as 2 to the power k plus 1, because we can simply ignore this minus 1. If you just ignore minus 1, you have to just put this less than symbol. Give me a second. I don't know, pen doesn't work. Good. This is that, that is that, that is that. I have to emphasize this symbol, and then you can ignore this minus 1. All right. Now we going to make the other side of the inequality. You could write 2 to the power k like this, 2 to the power k here, and then you have 2 to the power k here, and then you have these additional terms. Okay, you have these additional terms. All right, so you could do this, because the inequality here is less than or equal to. All right, so this equals that, and then you have additional terms. Actually, this entire thing equals this entire series equals n, Okay, then you have the lower bound. Then you have the lower bound like this. All right. N is greater than or equal to 2 to the power k, which is given by that formula. All right, let me make this a little bit bigger. All right, now just consider this inequality. This inequality is similar to property 11.4.2. I just go back to that property right here. 11.4.2. Now we are going to use that property again over there. Once you use this property, you could write k equals flow function of log n to the base 2. All right. Okay, this is k actually. This is k. What you need is number of binary digits that can be used to represent this number. Actually, the number of binary digits are represented by the upper bound. Okay, it is represented by the upper bound. All right, so it is actually k plus 1. Let me mark it here using a different color. This is actually number of binary digits. All right, which is k plus 1. Now it should be k plus 1, which is the flow function of log of n to the base n plus 1. Okay, so this is the answer for the question. All right, so let's move to the next example. The next example asks, how many binary digits are needed to represent 52,837 in binary notation? All right, so it is actually given by this result, which is we have already proven, which is log of 52,837 to the base 2, and then at the end you have to add 1. Okay, so this is actually let me write it here. This is actually log to the base 2 52,837 and get the flow function and then plus 1. All right, so that's what we're going to get here. But I wrote a little bit extra information for you to understand. And let me read that information. If you compute the logarithmic with base 2 using the formula that, and a calculator or a computer that gives you approximate values of algorithms with base 10. All right. So the thing is, computing logarithms with base 2 is hard, because that is not facilitated by a basic calculator. So you need a scientific calculator for that. But still, you could just do this small modification to compute this value to the base 2, log to the base 2. Okay, what we have done here is, this is what we have to find. This is what we have to find. Instead of that, what we do is we just replace this base. We replace that base by this base and this base. Okay, both are the same base, and this is actually a law in logarithms. I don't know whether you can remember this. You have learned this in Calc 1. If you have something like log a here, b here, and then this can be written down as log c here, b here, log c here, a here. All right, so here a, here a, here b, here b, this c is extra. Okay, that format should be there. So you can just transform the given logarithmic function to a different base. Since base 2 is hard to compute, you just transform it to the base 10 because 10 is convenient. All right, let me mark it here, and this is supported by that. All right, and then you just find this one using a calculator, find that one using calculator, substitute both here, and then find the answer. Okay, now what you have to do is you have to get the flow function of that, like I explained earlier. Here you see you have to get the flow function of that. So this is the flow function, and then you have to add 1 to that. You have to add 1 to that. Okay, so the answer should be 16. There should be 16 binary digits for this problem. Okay, in order to represent 52,837, you should need 16 binary digits. All right, so let's move to the next example. Okay, this is the second application using logarithms to solve recurrence relations. A class of recurrent relations that is very important in computer science has solutions that can be expressed in terms of logarithms. One such recurrent relation is discussed in the next example. Alright, so this is the example that we're going to discuss. Example 11.4.4. A recurrence relation with a logarithmic solution. So this is the given recurrent relationship to you. It says a1 equals 1 and ak equals 2 times a times the floor function k divided by 2. Use iteration to guess an explicit formula for this sequence. Alright, so here we have the solutions. So you already know that a1 equals 1, which is given right here, and then you have to find the rest of the terms. a2 equals a times a2 equals 2 times a 2 over 2 floor function. 2 over 2 is 1, floor function of 1 is 1, which is right here. So you know a1 is that, which is 1, then 2 times 1 is 2. All right, and then in the next term a3 equals 2 times a floor function 3 over 2. 3 over 2 is 1.5. Floor function of 1.5 is 1. Now a1, you know a1 already, which is 1, then it is 2. Then go to the next line, a of 4, which is 2 times a floor function 4 divided by 2. 4 divided by 2 is 2. The floor function of 2 is 2. And a2 is 2. Then 2 times 2 is 4. Alright, then here a5, which is 2 times 5 over 2. The floor function 5 over 2 is 2.5. The floor function of 2.5 is 2. And then is 2 times 2 is 4. So you can keep on doing that. So you can just get these values. Alright, you can get these values. So the nice thing is there's a pattern in these values. There's a pattern in these values. So this is a single value. You could just write it as 2 to the power 0. And then this is, all these values are 2's. You could write it as 2 to the power 1. And all these are 4's. You could write them as 2 to the power 2. And all these are 8's. You could write it as 2 to the power 2, and so on. Okay, they just go like blocks. There's a small note here. Note that in each case, when the subscript n is between two powers of 2, okay, the subscript between two powers of 2, an equals to the smaller power of 2. All right, that means let's say this subscript, which is 4, actually this subscript 4 is between 2 to the power 2 and 2 to the power 3. All right, this subscript 6 is in between 2 to the power 2 and 2 to the power 6. This subscript 7 is in between 2 to the power 4 and 2 to the power 2 and 2 to the power 3. Okay, then let me read this paragraph, this sentence again. Note that in each case, when the subscript n is between two powers of 2, an equal to the smaller power of 2. Then the solution equal to the smaller power. Here the smaller power is 2 to the power 2. In this interval, the smaller power of that one is that. So then all the values here is 4, which is 2 to the power 2. All right. So let me explain that again. Now let's go to the maybe the next block. Here n is 9. N is 9, which is between, which is in this block. All right, between 2 to the power 3 and 2 to the power 4, but the corresponding value, which is 8, is actually 2 to the power 3. That's what's given here. Okay, you can read and understand. Okay, there's a nice pattern which I just explained right here. All right, let's say a different number, maybe that n is 8, a of 8. That value is between this and that, 2 to the power 3 and 2 to the power 4. The corresponding solution or the answer for this case should be just the lower bound, which is 2 to the power 3. Okay, this is a nice pattern that you see here. Because of this reason, we could write n is actually in between 2 to the power I and 2 to the power I plus 1. Okay, n is in between 2 to the power I and 2 to the power I plus 1. Then by using that property, can remember we use a property. You can just use that property, which is 11.4.2. All right, give me 1 second. If this happens, then what we observed above is an equals the lower bound. An equals the lower bound. Let me mark the lower bound, which is right there. Okay, n equals the lower bound. Now, since n satisfies the inequality, this inequality that we learned before, by using the property 11.4.2, you could write I equals flow function log of n to the base 2. All right, you know the value of I here. Now you could write an, which is right here. You could write an as that 2 to the power, you replace I by this thing. Okay, you replace I by that thing. Okay, I equals log of flow function. I equals flow function of log of n to the base 2, which is right here. So this is the corresponding solution for an. Okay, what is given to you is a recurrent relationship. This is a recurrent relationship. What you get at last is just a function for an. This is not a recurrent relationship, which is not a recurrent relationship. All right, so the Another application of logarithmic function is for a given recurrent relationship. For a given recurrent relationship, you can get the explicit formula. Okay, you can get the explicit formula. All right, so that is end of the class. Thank you very much.